At the edge of imagination there is a distance so small that ordinary language almost fails, yet tonight the calm narration moves toward it with patient steps as if walking down a long, dim corridor of scales, from the largest structures in the cosmos to the tiniest tremors of space itself. Far above any listener, galaxies drift on rivers of dark matter clusters, gather like slow-moving islands of light, and the afterglow of the first fire of the universe still hums across the sky as a faint sea of microwaves. Within those galaxies, stars burn in quiet fusion, planets circle in slow, predictable arcs, and on one fragile world, instruments wait in the dark, tuned not only to the vastness of space, but to a very different frontier, the frontier of the incredibly small. In laboratories lit by the steady glow of monitors, beams of particles travel through evacuated tunnels. Crystals sit beneath polished lenses, and mirrors hang in vibration, isolated chambers that feel almost like observatories, pointed inward instead of outward. Every device is built around a simple rule of nature, a rule that has guided explorers since the first glass lens. To see smaller details, there must be higher energy, shorter waves, sharper probes. The same universe that stretches into clusters and filaments also hides its structure in layers that fold inward from cells to molecules, from molecules to atoms, from atoms to nuclei, from nuclei to particles that do not have familiar shapes at all, only probabilities and interactions. The narration follows that descent slowly, letting each level of structure settle like a quiet breath before moving on. A hair is wide, a cell is smaller, a bacterium smaller still, until the world that seems continuous at ordinary scales begins to dissolve into discrete units, each separated by empty space that is not truly empty. Under an optical microscope, there is already a feeling of crossing a boundary. The colors of familiar light scatter from membranes and fibers, revealing shapes that no unaided eye has ever seen, yet even here, the same limitation appears. Visible light has its own boundary encoded in its wavelength. The gentle waves that paint sunsets and wash across oceans cannot resolve an atom. They are too broad to thread through such a narrow scale. When scientists turn to electrons as probes, accelerating them so that their matter waves shortened and sharpened, a new realm opened. Viruses, atomic lattices, the regular geometry of crystals all emerged in clarity, as if the fabric of matter were being slowly brought into focus. This achievement, though, carried a hint of a deeper puzzle. Each improvement in resolution required feeding more energy into particles, pushing them faster, compressing their associated waves into smaller packets. At nuclear scales, the energies became immense compared with everyday experience, yet the urge to look deeper remained. Protons were found not to be uniform drops of charge, but stormy regions filled with quarks and gluons, their interactions described by the dense language of quantum chromodynamics. Experiments at long linear tunnels in California and great circular machines on the border between France and Switzerland mapped this inner landscape by watching how electrons and other projectiles scattered when they struck protons and nuclei, like rain revealing the shape of stones it splashes against. With each increase in beam energy, the effective wavelength of the probe shrank, and the picture of matter gained finer texture. From a distance, this progress looks smooth, almost inevitable, a staircase of insight leading steadily downward toward smaller scales. Yet hidden in the mathematics of gravitation and quantum mechanics is a quiet warning that the staircase cannot continue forever. The same energy that allows a probe to resolve smaller distances also contributes to gravitational attraction, because energy and mass are aspects of one quantity. Concentrate enough energy into a tiny region and the geometry of space begins to curve. concentrate still more, and that region can in principle collapse behind a horizon from which light cannot escape. The act of examining a region too aggressively causes that region to seal itself off, as if the universe were gently closing a door simply by following its own rules. This is where the smallest meaningful distance, the scale known as the Planck length, appears not as a decorative number in a textbook, but as a boundary implied by the logic of the laws themselves. At a length of about 1.6 times 10 to the power of minus 35 meters, space is no longer expected to behave like a smooth stage. Quantum uncertainty and gravitational curvature become equally strong, and the familiar concepts of position and duration weaken. Below this scale, no instrument built from known physics can define what it means for 2 points to be separate, because the energy required to probe that separation would create curvature so intense that the points themselves dissolve into a foam of possible geometries. Tonight the narrative rests at this threshold like a traveler pausing at the edge of a mist-covered canyon, aware that the terrain beyond cannot be drawn with ordinary lines. Instead of forcing an answer, the story circles the boundary with patience, tracing how telescopes, microscopes, particle colliders, and theories all point toward the same mysterious frontier, where looking more closely blurs rather than clarifies, and where distance itself begins to feel like a provisional idea rather than an unshakable fact. In that quiet recognition, curiosity does not end. It simply changes direction, turning from the question of how small things are to the deeper question of what it means for anything to have size at all. In the soft dark of a laboratory at night, instruments rest in ordered rows, all built to ask what lies beneath surfaces that ordinary sight calls solid and continuous. Glass microscopes were the first of these eyes. Their curved lenses bend visible light into fine points, where cells, fibers, and tiny organisms come into focus, revealing that familiar materials are built from smaller structures layered within one another. Yet an invisible boundary is already present. Visible light flows in waves that are hundreds of nanometers long, each crest broader than an atom. When such light touches matter, it can outline details no smaller than its own wavelength. Anything finer washes into a blur. The atom remains real but unseen, hiding behind a curtain woven from the same light used to seek it. From this limit, a rule emerges. To see smaller, a shorter wave is needed, and to create a shorter wave, higher energy must be used. Low energy waves are gentle but coarse. High energy waves are sharp but intrusive. Beams of more energetic photons, such as those used in X-ray crystallography, have wavelengths short enough to sense atomic spacing in crystals. They produce patterns that encode how atoms are arranged, while at the same time carrying enough energy to ionize atoms and damage the structures they reveal. The more sharply they draw the picture, the more they threaten to erase it. The search for a probe that is both fine and relatively gentle leads to a surprising insight. Matter itself can act as a wave. When electrons are aimed at thin crystals, the scattered pattern on a screen forms bands and rings like ripples from overlapping waves. The only way to understand this is to accept that an electron carries a wavelength linked to its momentum. Increase its energy and that wavelength shrinks. This wave nature of matter makes a new kind of microscope possible. In an electron microscope, streams of electrons are accelerated and steered by magnetic fields. Their wavelengths can be tuned by adjusting their energy short enough to explore atomic scales, yet low enough that they do not always tear the sample apart. In their images, solids no longer seem featureless. Grains defects and individual rows of atoms appear like distant cities coming into view from high altitude. The same guiding rule still stands. Higher resolution demands higher energy. As electrons are pushed to greater speeds, their wavelengths shorten and the details they can resolve grow finer, but their collisions become more violent. At high energies, electrons can knock atoms from their sites or deposit enough energy in a tiny region to change its phase. Even before gravity is considered, there is a sense that looking too closely comes at a cost. The narrative now steps from tabletop instruments to the scale of particle accelerators machines that circle beneath fields and towns. In these rings and tunnels, protons and electrons travel close to the speed of light inside evacuated pipes guided by magnets. Instead, they reveal structure through scattering. When a fast electron or proton strikes another particle, the angles and energies of the fragments carry information about what was inside. Experiments at long linear accelerators show that protons do not behave like smooth drops of charge. They scatter projectiles as though built from smaller centers of momentum, later described as quarks, held together by the strong nuclear force. Once again, a deeper layer is uncovered, and once again the price is higher energy. To probe the atomic nucleus requires beams with millions of electron volts. To see quark structure requires billions. Each step down the staircase of scale demands a leap upward in the energy of the probes. A quiet question rises from this pattern. If every new layer requires more energy to reveal, does the climb ever end? The same mathematics that relates wavelength and energy points toward gravity for an answer. In general, relativity, energy, and mass are two faces of one quantity that bends space-time. A particle accelerated to enormous energy does not only act as a sharper probe, it also contributes a stronger gravitational field to the region it enters. At familiar laboratory energies, this curvature is vanishingly small. In thought experiments that imagine energies far beyond any present technology, it grows significant. The geometry of space-time is no longer a passive stage. It responds to the very energy used to explore it. To estimate where this response becomes unavoidable, theorists compare two characteristic lengths. One is the quantum length, roughly the wavelength of the probe. The other is the gravitational length within which that same energy, if confined, would form a black hole. At low energies, the quantum length is large and the gravitational length is tiny, and the probe spreads through nearly flat space. As energy increases, the quantum length shrinks while the gravitational length expands. There is a critical scale at which the two lengths meet. At that point, concentrating enough energy to resolve a region that small would also cause that region to collapse behind a horizon. Beyond this scale, trying to sharpen the view only deepens the gravitational well. This meeting of lengths defines the Planck scale where quantum uncertainty and space-time curvature have equal weight. It is far beyond the reach of any present collider or microscope, yet it stands as a quiet instruction written into the equations themselves. The universe allows vision to sharpen only until these two curves cross. Past that crossing, the dream of infinite resolution is replaced by a different kind of clarity, the realization that the same laws that open the microscopic world also draw a soft boundary around its deepest depths. In the quiet progression from atoms to nuclei and then to the particles inside those nuclei, there comes a moment when the description of matter stops feeling like a catalog of solid pieces and begins to resemble the study of a storm. In the middle of the 20th century, when scientists had already accepted that electrons orbit a compact nucleus and that this nucleus contains protons and neutrons, the picture still seemed relatively simple. Protons and neutrons were treated as small indivisible beads of mass and charge tightly packed in the heart of every atom. Yet as accelerators grew longer and magnets grew stronger, beams of electrons could be fired with energies high enough to probe these supposed beads themselves. In long linear tunnels, electrons raced almost at the speed of light before being directed into thin targets of hydrogen and heavier elements. Detectors surrounding those targets recorded how the electrons scattered each deflection an imprint of the electric and magnetic structure they had passed through. If the proton were truly uniform, the pattern of scattering would follow a smooth, predictable curve. Instead, the data showed something more intricate. Electrons sometimes bounced as if they had struck smaller, concentrated knots of charge inside the proton. Rather than a single lump, the proton behaved as though it contained several centers that shared its momentum. From these patterns, a new layer of description emerged in which protons and neutrons are composite objects built from quarks. Each proton holds three main quarks bound together by the strong nuclear force mediated by particles called gluons. The names are playful, but the physics is not. The equations that describe this force, gathered under the name quantum chromodynamics, show that at very short distances the quarks behave nearly free, while at larger separations the force between them grows stronger like an elastic band that resists being stretched. This has an unexpected consequence. It is effectively impossible to isolate a single quark. Any attempt to pull it away from its partners adds energy to the band of strong force between them, and when that energy becomes high enough, it is converted into new quark pairs that bind into fresh particles. The effort to see one building block alone simply creates more of the same kind of storm. In this way, even the interior of a proton refuses to offer a simple solid core. If it could be frozen in an instant, its interior would not look like three marbles sitting inside a shell. Instead, calculations and experiments suggest a dynamic sea of quarks and antiquarks of gluons that flicker into and out of existence, all exchanging momentum at nearly the speed of light. The proton is mostly space threaded by fields, its mass arising from the restless energy of these interactions more than from the bare mass of the quarks themselves. The closer the probes look, the more the proton resembles a miniature universe of activity rather than a featureless grain. This picture already hints that the notion of matter as tiny hard spheres is an illusion born of limited resolution. At each deeper level, structure becomes more about fields, excitations, and probability distributions than about concrete little pellets. Yet the same rule persists. To reveal the detailed pattern of that inner storm, experiments must drive projectiles to energies of billions of electron volts and beyond. The wavelengths associated with these probes become smaller than the size of the proton, allowing them to map how momentum is shared among the quarks and gluons. Plots of these distributions show that the so-called valence quarks, the three main constituents, carry only a fraction of the proton's total momentum. The rest belongs to a fluctuating sea of additional quarks and the gluon field that binds them. What looks simple at first glance becomes layered and subtle. This complexity raises new questions. Are quarks themselves fundamental, or are they in turn built from more basic entities that only appear at even higher energies? Proposals for such deeper components, sometimes called by names like prions, have been explored in mathematics, but have not yet found support in data. The reason is not only that no clear signal has appeared, but also that pushing to the necessary energies would demand machines far more powerful than any now operating, and that such energies approach a region where gravity can no longer be ignored. Even without gravity, there is a sense of diminishing returns. Each leap in resolution requires a disproportionate increase in technical effort, energy consumption, and experimental complexity. Detectors grow to the size of buildings, computing grids span continents, and still the innermost layer remains out of reach. When gravity is allowed to enter the story, the pattern takes on a sharper form. The proton already shows that matter at small scales is mostly energy in motion within a confined region. If one imagines compressing that region further, concentrating more energy into a smaller volume, quantum chromodynamics alone cannot describe the result. At extreme densities, the energy stored in fields and motion becomes so intense that its gravitational effect must curve spacetime significantly. In astrophysics, this logic leads to neutron stars and then to black holes when enough mass collapses. In particle physics, the same reasoning applied in reverse suggests that using extremely energetic probes to examine ever smaller regions would eventually create similar conditions in miniature. Past some critical energy, the act of trying to resolve a substructure of a quark could instead form a tiny horizon around the interaction point, hiding whatever lay inside. The proton, once thought to be a final indivisible unit, becomes one step in a chain whose lower end is not simply another particle, but a boundary where the geometry of space-time itself intervenes. This realization shifts the tone of the quest. The staircase downward is no longer expected to continue indefinitely through smaller and smaller grains. Instead, it appears to lead toward a floor made not of matter, but of fluctuating space-time, where the familiar distinction between particle and field inside and outside begins to blur. The scattering data that first revealed quarks thus carry a quiet double message. They demonstrate that deeper layers of structure exist, and they hint that the pattern of unveiling cannot be repeated without limit. Beyond a certain point, the next layer may not be a smaller component at all, but a different kind of description in which size, position, and even the concept of a distinct object are replaced by more abstract relationships between energy curvature and quantum uncertainty. Deep beneath fields and quiet villages on the border shared by France and Switzerland, a ring of technology rests inside the earth. Like a hidden circuit, its tunnels dark and cold, while most of the world sleeps above. This buried circle acts as one of the sharpest eyes turned toward the structure of reality. It is called a collider, yet in a deeper sense it behaves like a microscope, one that does not rely on glass or gentle beams of light, but on streams of protons driven to nearly the speed of light and then brought into head-on collision. The rule that sharper vision demands higher energy reaches a grand expression here. Inside evacuated pipes, two proton beams travel in opposite directions, guided by chains of superconducting magnets. Each magnet bends the particles just enough to keep them racing along the circular path. The magnets are cooled until electrical resistance nearly vanishes, and strong magnetic fields can persist without wasting energy as heat. In this environment, the protons circle the ring repeatedly, gaining a small increment of energy with each pass from radio frequency cavities that push them forward in synchronized pulses. As the energy climbs, so does the resolving power of the instrument. The wavelength associated with each proton shrinks far below the size of the atomic nucleus into a regime where quarks and gluons dominate. In the language of particle physics, each proton carries energy of several tera-electron volts, and when two beams meet in a precisely arranged crossing point, the total energy available in the collision reaches into the tens of tera-electron volts. For a brief instant, all of that concentrated energy occupies a region smaller than the nucleus of an atom. Space in that tiny region no longer behaves as a quiet background. The fields that fill the vacuum respond, including one that rarely draws attention in everyday life, yet shapes the structure of matter, the field associated with the Higgs boson. In ordinary conditions, this field permeates space with a constant non-zero value, endowing certain particles with mass as they move through it. The collider shakes this field locally by pouring energy into a single point, turning the disturbance into a brief quantum excitation. The Higgs boson appears not as a long-lived object, but as a ripple that decays into other particles almost as soon as it forms. Detectors built around the collision points are arranged in layers, each tuned to register different kinds of fragments. Inner trackers record the paths of charged particles as sequences of hits in silicon. Calorimeters measure how much energy these fragments deposit as they slow and stop, while outer systems sense particles that pass through material almost unaffected. All of this information flows into data systems that reconstruct each collision as a branching history, inferring what must have existed in the first instance from the spray observed afterward. Among billions of events, a small minority carry the signature of a Higgs boson revealed not by catching it directly, but by seeing the characteristic pattern of its decay products. The confirmation of this particle shows that the field it represents is real, and that the standard model of particle physics, a framework of symmetries and interactions, describes nature accurately across a wide range of energies. Yet even in this triumph, there is a sense of incompleteness. The collider confirms that the known pattern of particles and forces holds up under intense scrutiny, but it also reveals no obvious path beyond that pattern. Plans for upgrades focus on increasing luminosity, the number of collisions per second, rather than on radically higher energies, because the practical challenges of pushing beams further grow severe. When the collider is viewed through the lens of the Planck scale, its power and its limits come into sharp relief. The energies reached in these collisions, impressive by human standards, are still many orders of magnitude below those required to probe distances on the order of the Planck length. The wavelength associated with a proton at the highest energies of the collider is tiny compared with an atom, but still vast compared with that ultimate scale. In effect, the collider is an extraordinarily fine microscope that nonetheless stops far short of the boundary where quantum mechanics and gravity fully intertwine. Even so, it serves as a bridge. Within its detectors, space and time are sampled at intervals small enough that familiar intuitions falter, and the vacuum reveals that it is filled with virtual excitations, pairs of particles that flicker into and out of existence according to quantum rules. All of these phenomena hint that the vacuum is not an empty stage, but an active medium whose properties shape what can exist. Standing back, the collider can be seen as a rehearsal space for the cosmos itself. By recreating in miniature and for brief moments the energy densities that prevailed fractions of a second after the Big Bang, it offers glimpses of how fields settled into their present configurations. The nature of dark matter remains unknown, the origin of cosmic inflation is still uncertain, and gravity continues to stand apart from the quantum tapestry woven so precisely for the other forces. The ring beneath the fields therefore plays a dual role. It is both an instrument for measurement and a reminder of the limits written into current understanding, showing how far the method of using higher energy to see smaller can be driven in practice, and standing as a quiet marker along the road to the Planck scale, far below the energies it can reach, where a different kind of description must eventually replace the idea of particles moving through a smooth continuum. Section 5. In the unfolding picture of smaller and smaller scales, gravity at first appears as a distant background presence important for planets and stars, but irrelevant inside laboratories, where particle beams and delicate crystals dominate the scene. Yet the same equations that describe how planets fall towards stars also assign a gravitational field to every form of energy, no matter how small the region it occupies. This quiet fact turns the familiar rule of sharper vision through higher energy into something more subtle and eventually more restrictive. At ordinary experimental energies, the effect is imperceptible, so it is natural to treat gravity as absent, to imagine that the geometry of space remains perfectly flat and indifferent while quantum particles glide and scatter upon it. Now the calm focus shifts to a thought experiment that stretches this logic far beyond the reach of any machine to see what the laws themselves predict. When the energy of a probing particle grows so large that its gravitational imprint can no longer be ignored. Imagine a single quantum of light, a photon chosen as a probe. To resolve a very small region, its wavelength must be at most comparable to that region. The relation between wavelength and energy means that as the desired resolution shrinks, the required energy climbs. For modest resolutions, this poses no conceptual problem, but if the target region is made smaller and smaller, the energy of the photon rises without apparent bound. At some stage, the energy concentrated in the tiny wave packet becomes so large that according to general relativity, space-time near the photon curves significantly. There exists for every amount of energy a characteristic radius, the Schwarzschild radius, within which that energy, if confined, would form a black hole. As the photon energy grows, this radius expands. The resolving power of the photon improves because its wavelength shortens, yet the region of intense curvature around it also grows because of its increased energy. The quantum tendency toward finer localization and the gravitational tendency toward horizon formation move toward each other. The critical point arrives when the target size, the wavelength of the photon, and the Schwarzschild radius of its energy all become comparable. Beyond this point, any further attempt to sharpen the view by increasing energy only strengthens gravity's grip. Instead of revealing more structure, the probe now threatens to create a tiny black hole that encloses the region under study. The smallest meaningful distance appears here as a balance point rather than an arbitrary cutoff, because if one insists on a resolution finer than this, the region from which information could emerge is hidden behind an event horizon. The same reasoning applies in quieter form to massive particles. Electrons, protons, or heavier projectiles can be accelerated to enormous energies to act as probes, but the more energy they carry, the more intense their gravitational field becomes in the frame where they are briefly localized for an interaction. At extreme energies, any attempt to confine them to a region smaller than their associated Schwarzschild radius again risks forming a microscopic black hole. The Planck length, around 1.6 times 10 to the power of minus 35 meters, marks roughly the scale where this balance is expected to occur, where quantum uncertainty and gravitational collapse compete on equal terms. No direct experiment has reached anywhere near this regime, and none is expected to, not because engineers lack imagination, but because the energy required would exceed what could be stored in any conceivable machine. Thought experiments, however, remain free to wander there, guided by equations instead of magnets and cables. They show that the path of using ever higher energies as a microscope has an endpoint set by the structure of space-time itself. What was once a fluid continuum of possible positions becomes blurred by its own curvature. Distance ceases to be an absolute quantity that can be subdivided without limit, and becomes instead a concept with a built-in graininess imposed by the combined demands of quantum theory and general relativity. It suggests that there may be no meaning to the question of what lies at a separation smaller than the Planck length in the usual sense of distance. Theories that attempt to unify quantum mechanics with gravity often build this idea into their foundations. In some approaches, such as those that propose a generalized uncertainty principle, the familiar Heisenberg relation between position and momentum acquires extra terms that prevent the uncertainty in position from shrinking below a minimum. In others, the geometry of space-time is treated as composed of finite units that cannot be subdivided. Regardless of the specific framework, the same soft boundary reappears. The universe allows observation to penetrate down to a scale where quantum fluctuations and curvature weave a restless foam and then withholds further clarity. Instead of an endless slatter of smaller particles, the picture that emerges is of fields, energy, and geometry entangled in such a way that trying to isolate them more sharply only deepens their mutual influence. Gravity, which seemed at first a distant player in the microscopic world, reveals itself as the final arbiter of how far the method of seeing by scattering can be pushed. At human scales, it keeps planets in orbit and shapes the paths of falling objects. At ultramicroscopic scales, it shapes the very definition of what it means for one point to be distinct from another. The closer the gaze tries to draw its circle of light, the more space-time itself bends that circle closed until the act of looking becomes inseparable from the fabric being observed. In the layered story of scales, there comes a turning point where a single number built not from experiment, but from the constants of nature themselves begins to guide the imagination. That number is the length commonly called the Planck scale, a distance so small that the step between any human-made measurement and this frontier feels more like a fall than a stride. It arises when three pillars of physics are combined: the speed at which light travels in empty space, the constant that measures the graininess of quantum action, and the constant that sets the strength of gravity. When these are woven together into a unit of length, the result is a scale of about 1.6 times 10 to the power of minus 35 meters. No instrument has ever reached it, and none is expected to, yet it appears in equations as a natural dividing line between regimes where familiar theories work well and regimes where they struggle. At lengths much larger than this scale, general relativity describes space-time as a smooth manifold whose curvature responds to the distribution of mass and energy, while quantum field theory describes matter and forces as excitations of fields that live upon this manifold. The two frameworks can coexist as long as gravity remains weak on the scales where quantum fluctuations are important. Near the Planck length, however, this separation dissolves. Quantum uncertainty shakes every quantity, while gravity amplifies the effect of energy on curvature, so that the geometry of space-time itself begins to fluctuate. The calm image of a continuous fabric bends into something more restless, a picture often called quantum foam. In this foam, distances and durations cannot be pinned down sharply. The very notion of a straight line between two events loses precision because the metric that measures such lines is no longer stable. The early universe passed through this regime in its first instance, long before atom stars or even protons formed. Modern cosmology, anchored by observations of the cosmic microwave background and the distribution of galaxies, traces the history of expansion back to an era when the universe was incredibly hot and dense, but still many orders of magnitude larger than the Planck length. Before that, the equations extrapolate into a region they were not designed to describe. The singularity that appears at the start of classical Big Bang solutions is a signal of this breakdown, not a literal point of infinite density, but a boundary beyond which the classical picture cannot be trusted. In this sense, the Planck scale is less a physical wall and more a horizon in theory space beyond which a new description must take over. This realization has inspired several attempts to quantize gravity. In string theory, the fundamental objects are not point particles, but tiny one-dimensional strings whose typical size is close to the Planck length. These strings cannot be compressed arbitrarily. When energy is poured into them, they vibrate in more complex modes rather than shrinking into smaller points, so the theory contains a built-in minimal length below which the concept of distance loses its ordinary meaning. Loop quantum gravity approaches the problem from a different angle, starting from the equations of general relativity and reformulating them in a way that can be quantized. In this framework, areas and volumes come in discrete units. Space is represented as a network of finite loops, and the smallest non-zero area is of the order of the Planck length squared. Both perspectives, despite their differences, point toward a universe in which there is no sensible way to talk about distances smaller than a certain grain. This does not mean that space is made of little rigid cubes, but rather that some combinations of measurements simply cannot be defined with arbitrary precision. Thought experiments that combine the uncertainty principle with gravitational collapse reach similar conclusions. They suggest that any attempt to localize a particle within a region smaller than the Planck length would require so much energy that a black hole forms cloaking the region from observation. In that view, the Planck length is a kind of limit on information. It tells how finely nature allows reality to be divided while still maintaining a meaningful distinction between here and there, before and after. Some ideas tie this minimum scale to the way information is stored on horizons where the amount of information appears to scale with area measured in Planck units rather than with volume. From this angle, the Planck length sets the size of the smallest information-carrying patch on any boundary. The picture that emerges is both restrictive and suggestive. Restrictive because it denies the possibility of an endlessly divisible continuum, suggestive because it implies that many apparent infinities in physics may be artifacts of pushing continuous models beyond their domain of validity. Instead of a universe that becomes ill-defined at ever smaller scales, there may be a natural end to the ladder of distances, a floor where geometry itself becomes quantized or emerges from something deeper. Whether the Planck length is truly the last meaningful scale or a signpost toward an even more radical description in which space and time themselves dissolve into networks of relationships remains unsettled. What is clear is that this tiny number derived from fundamental constants acts as a quiet reminder that even in a cosmos of vast galaxies and deep time, there exists an opposite extreme where size almost ceases to be a useful word, and where the language of physics must shift from lines and surfaces to more abstract notions of information entanglement and structure without background. Long before gravity is invited into the microscopic story, quantum mechanics already carries within it a quiet resistance to the idea of perfect sharpness. In the early 20th century, Werner Heisenberg formulates a principle that seems at first like a technical detail and slowly reveals itself as a profound statement about how reality presents itself. According to this principle, the more precisely the position of a particle is known, the less precisely its momentum can be known, and the more precisely its momentum is defined, the more diffuse its position becomes. Particles at small scales do not move like tiny stones following exact trajectories. They inhabit clouds of possibility described by wave functions whose spread cannot be compressed to a single point. This uncertainty is not blamed on flaws in instruments or clumsiness in technique. It is built into the structure of quantum states themselves. Even in an idealized experiment with perfect detectors, there remain pairs of quantities that cannot both be pinned down beyond certain limits. Position and momentum form one such pair, energy and duration another. The mathematics encodes this through commutators and Planck's constant, but the physical message is simple. Nature at small scales does not permit perfect localization without a cost in the clarity of motion. To visualize this quantum theory often turns to a thought experiment, not as a literal laboratory plan, but as a way of clarifying relationships. Imagine trying to locate an electron by scattering light off it. A photon with a long wavelength is too spread out to mark the electron's position precisely. It produces only a vague indication of where the particle might be. A photon with a shorter wavelength can in principle reveal the position more sharply because its crests and troughs are more closely spaced. However, a shorter wavelength corresponds to higher energy. When such a photon strikes the electron, it transfers momentum, disturbing the electron's motion more severely. The experimenter can choose a gentle, low-energy photon that leaves the momentum almost unchanged but provides a fuzzy position, or a violent, high-energy photon that gives a sharp snapshot of position while scrambling the momentum. No strategy allows both to be simultaneously precise. In standard quantum mechanics, space-time in this story is treated as a fixed, smooth background. The photon carries energy and momentum, but the geometry through which it travels remains flat and passive. When gravity is added to the picture, this assumption can no longer be kept. Energy curves space-time no matter how it is packaged. The photon that probes the electron now possesses not only a wavelength and momentum, but also a gravitational field. At low energies, this field is negligible. The geometry is effectively unchanged. As the photon energy increases to achieve finer resolution, its gravitational influence grows. The subtle bending of space-time around it becomes part of the measurement. A second layer of disturbance is added not just to the electron, but to the very coordinates used to describe its position. The same thought experiment that illustrated Heisenberg's principle can be extended. A photon of extremely high energy is aimed at a region of very small size with the aim of pinpointing a particle's location with extraordinary accuracy. Quantum mechanics alone says that nothing forbids this, apart from the growing uncertainty in momentum. General relativity adds a further condition. If the energy of the photon within that confined region exceeds a certain threshold, the curvature of space-time becomes large enough to form a tiny event horizon. The region from which information can escape shrinks, and beyond a critical point, a microscopic black hole forms. Instead of revealing a sharper position, the measurement creates a gravitational curtain hiding the very place being examined. From this union of quantum and gravitational reasoning arises the idea of a generalized uncertainty principle. It keeps the original quantum effect at low energies, where increasing the precision of position measurement still increases the uncertainty and momentum in the familiar way. At higher energies, an additional term appears reflecting the growing role of space-time curvature. The consequence is that there exists a minimum uncertainty in position that cannot be reduced by any choice of probe or technique. Attempts to compress the wave packet below this scale are countered by gravitational collapse. In many formulations, this minimum is of the order of the Planck length. The Planck length therefore enters not only as a scale at which theories break down, but as a limiting accuracy of measurement, a smallest grain of space in an operational sense. No observer, however patient or ingenious, can design an experiment that distinguishes 2 points closer together than this. This does not necessarily mean that space is literally composed of cubes of Planck size. It does mean that the combination of quantum uncertainty and gravitational reaction erases the operational meaning of such subdivisions. Some candidate theories of quantum gravity reflect this limit in their structure. In string theory, a string cannot be probed at distances smaller than its own length. Additional energy merely excites higher vibrational modes and stretches the object. The effective resolution stops improving and begins to blur. In loop quantum gravity, the operators corresponding to area and volume have discrete spectra with smallest non-zero values, so that there are finite quanta of geometry. Across these diverse approaches, a recurring pattern appears. The microscopic world resists attempts to define positions with arbitrarily fine precision. Information about location is not infinitely compressible, it is bounded by the interplay between indifferent quantum spread and active gravitational feedback. This has implications for black hole physics as well. The entropy of a black hole, a measure of the information that could in principle be hidden behind its horizon, turns out to be proportional not to its volume but to its surface area, measured in Planck units. Each patch of area of roughly Planck size appears to represent one elementary unit of information. The same minimal length that arises from the generalized uncertainty principle thus also measures the density of information that space can hold. As the narrative drifts over these ideas, the image of reality shifts gently. Instead of a continuum where any point can be separated from any other by a sharply defined distance, the world at its deepest levels behaves like a system where attempts to define such separations too precisely cause the concept to unravel. Quantum uncertainty and gravity, once thought to live in different domains, work together to draw a soft halo around every event, ensuring that the notion of position remains slightly blurred, and that beneath a certain scale the word distance becomes less about meters and more about what information can and cannot be drawn out of space-time. Before the idea of strings enters the story, the microscopic world in many theories is populated by idealized points. Electrons, quarks, and other particles are treated as having no size at all, occupying positions that can in principle be brought arbitrarily close together. This simplification works well at everyday energies, where the distances probed are large compared with any conceivable internal structure. Calculations of electromagnetic forces and nuclear interactions, while subtle, produce answers that match experiments with remarkable precision. Yet when these point particles interact at extremely high energies, the mathematics begins to show strains. Quantities that ought to remain finite instead drift toward infinity, signaling that the model is being pushed beyond its natural domain. Methods of renormalization tame many of these infinities for the non-gravitational forces reshaping the theory so that measurable predictions stay finite and accurate. Gravity, however, resists this treatment. When one tries to combine general relativity, which describes gravity as the curvature of space-time, with quantum field theory based on point particles, the infinities do not cancel cleanly. At very short distances, the gravitational field of a point particle becomes singular, and attempts to quantize this field produce divergences that cannot be absorbed by any simple redefinition of parameters. It is as if the assumption of point-like structure creates a knot in the mathematics, one that grows tighter the harder it is pulled. Into this difficulty steps a different image of fundamental objects. Instead of points, imagine that the basic excitations are tiny one-dimensional strands, strings that can be open like short segments or closed like loops. These strings are not infinitely thin lines. They possess a characteristic length typically taken to be comparable to the Planck scale. When energy is added to a string, it does not shrink into a smaller point. Instead, it vibrates in more complex patterns. Each pattern of vibration corresponds to what, at lower energies and larger scales, appears as a distinct particle. Some modes behave like electrons, others like quarks, others like carriers of the known forces. One particular vibrational mode has the properties expected of a quantum of the gravitational field. In this way, gravity emerges not as a separate add-on, but as an intrinsic part of the dynamics of strings. The key feature for the question of resolution is that strings soften interactions at short distances. When 2 point particles scatter, the interaction is concentrated at a single space-time point, which encourages the growth of ultraviolet divergences. When two strings interact, they merge and split over a finite region. The interaction is spread along their length, smearing out the would-be singularity. At high energies, scattering amplitudes decrease rather than blow up. The extended nature of strings therefore acts as a built-in regulator, preventing the theory from probing arbitrarily small scales in a way that would generate uncontrollable infinities. From the point of view of an observer using strings as probes, the familiar rule of higher energy, giving finer resolution, changes character near the string scale. At moderate energies, increasing the energy of a string does shorten its effective wavelength, allowing it to resolve finer details, just as with particles. As the energy approaches the scale set by the string tension, a transition occurs. Further increases in energy do not compress the probe into a smaller region. Instead, they excite higher vibrational modes and can even stretch the string so that the object becomes effectively larger. In some analyses, a duality appears between very small and very large distances, such that physics at a radius smaller than the string length can be mapped to physics at a larger radius. This duality suggests that there is no operational meaning to distances below the characteristic string length, because any attempt to probe such regimes simply reproduces behavior already accessible at larger scales. The string length, often of the order of the Planck length, becomes a lower bound on spatial resolution, built not from imposed cutoffs, but from the dynamics of the theory itself. An additional layer of structure appears when strings are allowed to vibrate not only in the familiar 3 dimensions of space, but in extra dimensions that are curled up so tightly they escape direct detection. The shapes of these compact dimensions influence which vibrational modes are allowed, and therefore which particles and forces are present in the low-energy world. Different choices of internal geometry lead to different effective physics in the large dimensions. In this sense, what appears as particle content and interaction strength at accessible energies is traced back to the geometry of spaces too small to be visualized in ordinary terms. Once again, the idea of probing smaller scales merges with the idea of exploring more intricate patterns of vibration and curvature, rather than simply finding smaller beads. Within this framework, the Planck length is not merely a scale where current theories break, but the scale where strings reveal their full character. Below it, the notion of a point loses its usefulness. Attempts to pinpoint locations more closely simply activate new modes and new dualities so that the map folds back on itself. Information about position is encoded not in finer and finer coordinates, but in the spectrum of possible vibrations and the topology of hidden dimensions. The infinities that plagued point-based approaches are avoided because the fundamental processes never focus energy into an exact point. Instead, they trace out smooth world sheets and space-time surfaces swept by strings as they move. Calculations performed on these surfaces remain finite under conditions where point-particle diagrams would diverge. For questions about quantum gravity, this behavior is particularly significant. Since one of the string modes behaves like a graviton, the hypothetical quantum carrier of the gravitational interaction string theory describes a quantum gravity from the outset. The same mechanism that softens collisions at high energy also softens the short-distance behavior of the gravitational field. Singularities that would appear in classical general relativity may be replaced in a full-string description by extended configurations where geometry is modified in a controlled way. The idea that black hole interiors, cosmological beginnings, or other extreme environments might be described without infinite curvature becomes thinkable within this picture. Yet for all its internal coherence, the string description remains largely untested experimentally. The energies at which stringy effects become dominant lie far beyond current accelerators, and the subtle imprints that might appear in cosmological observations or rare processes are difficult to disentangle from other possibilities. As a result, string theory occupies a curious position. It offers a mathematically consistent way to combine quantum mechanics and gravity, complete with a built-in minimal length and a rich space of possible universes, yet it has not yet been anchored by definitive data. Still, in the context of the question of how far nature allows resolution to be pushed, it illustrates one possible answer. Instead of an endless descent through smaller and smaller point-like constituents, there is a level at which the concept of a constituent changes. The universe at its deepest layer may be less like a pile of grains and more like a network of resonant threads where trying to zoom in beyond the string scale does not reveal new dots, but only new harmonies of vibration woven into the same underlying fabric. Alongside the image of vibrating strings, another picture of the deep structure of reality quietly develops, one that does not begin with new kinds of matter at all, but with the geometry of space itself. In this picture, gravity is not something to be added to quantum theory from the outside. Instead, the very fabric that bends and curves to produce gravity is given a quantum description from the start. General relativity has long described space-time as a smooth continuum where distances and durations can vary, but where the fabric itself has no granularity. Loop quantum gravity takes the opposite stance. It asks what happens if that fabric is treated as a system that can be quantized in the same way that light and matter are. The starting point is still Einstein's insight that gravity is geometry. Mass and energy tell spacetime how to curve, and that curvature tells objects how to move. But when the equations of this theory are rewritten in a form more suited to quantization, a remarkable pattern appears. The operators that correspond to geometric quantities such as area and volume do not admit a continuous range of values. Instead, they possess discrete spectra. There are smallest non-zero eigenvalues that set fundamental quanta of area and volume. Space in this view is not a continuous sheet, but a network of finite chunks. At scales much larger than the Planck length, these chunks are so small and numerous that the network is perceived as smooth, just as grains of sand merge into the appearance of a continuous beach when seen from a distance. At the Planck scale, however, the granularity is expected to become decisive. The mathematical structures that represent this quantum geometry are often called spin networks. In these networks, nodes carry quanta of volume, while links between nodes carry quanta of area. The pattern of connections and labels encodes the shape of space without reference to any higher backdrop. There is no underlying continuous grid upon which the network is drawn. The network itself is the geometry. Over time, these networks evolve into structures called spin foams, where the web of connections reshapes and flows. In this way, time is not an external parameter against which events are plotted. It is part of the evolution of the network itself. At large scales, when many quanta are involved, the average behavior of these networks can reproduce the smooth space-time of general relativity. In that sense, the familiar continuum emerges as an approximation valid when the coarse-grained view is sufficient. At very small scales, the fundamentally discrete nature of space becomes important. This discreteness has concrete implications for extreme environments. In classical general relativity, the equations that describe a collapsing star often predict a singularity at the center of a black hole, a point where curvature and density diverge, and where the theory ceases to make sense. Similarly, extrapolating the expansion of the universe backward in time leads to a singular beginning where densities become infinite. In loop quantum gravity, the presence of a minimal volume changes this picture. Quantum corrections to the classical equations become dominant at high densities and prevent complete collapse into a point. For cosmology, this leads to models in which the Big Bang is replaced by a bounce. A prior contracting phase reaches a maximum density set by the Planck scale, and then the quantum geometry causes a rebound into expansion. The singularity is replaced by a smooth transition through an extremely dense but finite state. Inside black holes, the same mechanism may replace the classical singularity with a region where quantum geometry is strongly excited, though the details remain an active area of research. For the question of resolution, the key point is that in this approach there is simply no way to define a geometric object smaller than the basic quanta. Areas and volumes cannot be subdivided indefinitely. The Planck length appears as the characteristic size of the smallest meaningful patches of surface and chunks of volume. Any attempt to probe smaller scales would encounter not a continuum to be carved more finely, but a lattice-like structure where further subdivision has no geometric meaning. This does not mean that the universe resembles a rigid crystal. The spin networks are not arranged on a fixed regular grid. Their connectivity and labels can vary, creating a flexible dynamic scaffold more like a woven fabric than a tiled floor. The discrete nature is not about straight lines and right angles. It is about the existence of smallest units that can still carry geometric information. Observationally, these ideas remain difficult to test. The Planck scale is far beyond direct access, yet there may be subtle footprints. If spacetime has a granular structure, very high-energy photons traveling across cosmological distances might experience tiny corrections to their speed or dispersion effects that grow cumulatively over billions of years. Searches for such energy-dependent delays in gamma-ray bursts have so far seen no clear signature placing constraints on how strong such granularity effects can be. In the cosmic microwave background, the afterglow of the early universe patterns of polarization could hold traces of a bounce or of quantum gravitational effects during the earliest moments of expansion. Future observatories may be sensitive enough to explore these possibilities. Even without definitive data, the conceptual shift that loop quantum gravity represents is striking. Instead of putting quantum fields on a pre-existing space-time, it treats spacetime as made of quantum entities. There is no stage separate from the actors. The stage is itself a cast of changing relationships. In this story, the question of how close 2 points can be brought together is answered by the structure of the network. Below a certain separation, nodes cannot be distinct. Links cannot carry smaller areas. The limit of resolution is woven into the connectivity of the web. This aligns with the idea arising from generalized uncertainty relations and holographic arguments that there is a finite amount of information that can be stored in any finite region proportional to its surface area in Planck units. The discrete units of area in loop quantum gravity could represent the pixels in which this information is encoded. Whether this specific framework ultimately describes nature or serves as a stepping stone toward a deeper theory is not yet known. What it does provide is a concrete example of how the smooth continuum of space-time, long taken for granted, may emerge from a more granular substrate. The Planck length thus appears again not as an arbitrary cutoff imposed to evade infinities, but as the natural size of the threads out of which the cosmic fabric is woven, and beyond which the notion of distance itself is replaced by a more abstract language of nodes, links, and the probabilities that govern their ever-shifting connections. As evidence from microscopes, colliders, telescopes, and theory accumulates, a quiet pattern emerges. The objects that are measured grow stranger with each new layer of resolution, yet a deeper change touches the background itself. Concepts that once seemed fixed, such as distance, duration, and location, begin to look less like fundamental ingredients and more like approximations. At everyday scales, the separation between 2 points can be written as a certain number of meters, and different methods of checking agree. General relativity refines this picture by allowing mass and energy to curve space-time, but the fabric it curves is still continuous. At atomic scales, quantum mechanics reshapes the behavior of matter, yet the wave functions of particles are defined over a well-behaved background with ordinary coordinates. As attention moves toward the Planck length, this division between objects and stage begins to dissolve. Quantum uncertainty starts to affect the metric itself, not just the particles moving within it. The question shifts. If distance loses its usual meaning at these scales, what can still be measured with clarity? A first hint comes from black holes treated as theoretical laboratories where gravity and quantum effects must be combined. Classically, an event horizon hides the details of what has fallen inside, leaving only a few macroscopic quantities visible. Quantum reasoning adds an entropy to the horizon, a measure of the number of microscopic states compatible with the same outward appearance. That entropy scales with the area of the horizon in Planck units, not with its volume. The information capacity of the region behaves as if it were stored on a surface. This pattern leads to the holographic principle, the proposal that a theory with gravity in some volume can be equivalent to a theory without gravity living on its boundary. A quantum field theory on the boundary can encode all the physics of a higher dimensional spacetime in its interior. Distances in the bulk correspond to patterns of correlation and entanglement in the boundary theory. Geometry emerges from the organization of information. Entanglement, the non-classical link between parts of a quantum system, becomes central. When subsystems are entangled, measurements on one influence the probabilities of outcomes in the other in ways that cannot be explained by ordinary separation alone. In holographic dualities, the amount of entanglement between regions of the boundary can be related to the area of certain surfaces in the bulk spacetime. Cutting the system into 2 parts and asking how entangled they are is roughly analogous to slicing the bulk and measuring the size of the dividing surface. Where entanglement is abundant and smoothly distributed, spacetime appears extended and connected. Where entanglement is sparse or fractured geometry pinches or fails to form, this suggests an inversion of the usual hierarchy. Instead of taking distance as primary and treating entanglement as a derived property, the more fundamental data may be the pattern of entanglement, with distance emerging as a convenient summary of which degrees of freedom are strongly or weakly correlated. 2 regions that share many entangled links behave as if they are close. 2 that share few behave as if they are far. In this view, measuring distance at the deepest level is equivalent to measuring correlation. The metric of spacetime becomes a map drawn from the web of quantum relationships. If so, the fading of classical distance near the Planck scale is not a loss of all measurable structure, but a change in what is natural to describe. Coordinates cease to be reliable once quantum fluctuations of geometry grow large. The entanglement pattern, however, remains well defined. Quantum states still carry precise information about how their parts are correlated even when no smooth underlying manifold exists. The Planck length would then mark the limit of applicability of geometric language, not the end of physics. Beyond it, descriptions in terms of information entropy and correlation would take over. As candidate theories of quantum gravity develop, some begin from the idea that space-time is not fundamental but emergent like temperature in a gas. Temperature is real and measurable, yet it does not exist at the level of individual molecules. It arises from collective behavior. In an analogous way, distance, duration, and even causality might arise from deeper structures of quantum information. At large scales where entanglement patterns vary smoothly, the familiar picture of a four-dimensional space-time with gentle curvature would appear. At very small scales where the underlying structure is coarse or highly tangled, the smooth picture would fail. There might be no single manifold on which all events can be plotted, only networks of relationships that approximate one when viewed from afar. In this perspective, the question of what can be measured when rulers fail receives a quiet answer. Correlations can be measured. Entropies and spectra can be calculated. Horizons can be assigned areas and temperatures that reflect information content. The Planck length remains a boundary for classical notions of distance, a scale below which attempts to sharpen location lead to gravitational collapse or quantum foam. Yet the story does not end at that boundary. The fabric that replaces familiar geometry is woven from relational data, from the way probabilities are linked across subsystems. Even when distance as a number of meters loses clarity, the network of who influences whom and by how much can still be described. In that network may lie a deeper order that continues to guide motion structure and evolution, even when the last reliable ruler has long been set aside. In the vast catalogue of ideas linking the very large to the very small, one theme returns quietly again and again. The universe places limits not only on what exists, but on what can be known in practice. Telescopes, particle colliders, cryogenic detectors, and delicate interferometers each open their own window, and together they form a kind of ladder spanning from galactic superclusters down toward the Planck length. No single instrument can cover this range, yet each rung informs the others. Observations made at cosmic distances sometimes reveal hints about the physics of the earliest instants, while controlled experiments at microscopic scales test the same principles in another guise. In this shared effort, the frontier where distance loses its classical meaning does not appear as an isolated curiosity. It influences how questions are framed at every scale. When astronomers use space telescopes to study the afterglow of the Big Bang, they infer that at very early times the universe must have passed through densities approaching those where quantum gravity becomes important. When gravitational wave observatories register the mergers of black holes, they measure how space-time responds to extreme curvature-setting constraints on theories that predict subtle deviations from general relativity. High-energy cosmic rays striking the atmosphere with energies far beyond those achievable in human-built colliders hint at acceleration mechanisms in distant astrophysical engines and at possible new physics in their interactions. In each case, the data are gathered far from the Planck scale, yet the interpretations reach toward it. Proposed modifications of uncertainty relations, minimal length effects, or granular spacetime can alter the propagation of light and particles over vast distances. Even a tiny departure from perfect smoothness multiplied by billions of years of travel could leave a detectable imprint in arrival time's energy spectra or polarization patterns. Searches for such signatures have so far found no clear, universally accepted signal, but they have narrowed the range of possibilities. The silence of the data in certain channels speaks as clearly as a detection would, telling theorists which versions of quantum gravity remain viable. The interplay between theory and observation becomes a slow, careful conversation. Equations suggest how space-time might behave near the Planck scale. Observations test whether echoes of that behavior ripple outward into regimes that can be measured. At the same time, the existence of fundamental limits encourages a shift in perspective. Instead of imagining an ultimate theory that yields exact predictions for every quantity, the focus moves toward understanding patterns, bounds, and emergent behaviors. Black hole thermodynamics, holographic principles, and entanglement-based pictures of geometry all express themselves as relationships between areas, entropies, and correlation strengths, not as catalogs of positions and velocities. What remains reliably measurable at all scales are these relational quantities. Correlators in quantum field theory, spectra of fluctuations in the cosmic microwave background, and timing residuals in pulsar arrays all encode how different parts of a system influence each other, rather than where exactly each part is in an absolute sense. The Planck length thus enters not as a sharp edge in data, but as a guiding scale in the structure of the laws that relate observable correlations. It tells how finely information can be packed, how densely states can be arranged, and how horizons store what falls behind them. Even if no direct imprint of Planck scale discreteness is ever seen, the requirement that any candidate theory reduce to known physics far above that scale while respecting these information bounds shapes its form. In this way, the unreachable frontier still exerts a quiet discipline on ideas. It also encourages a certain humility in the interpretation of measurements. Every ruler, clock, and detector is built within a world where space-time behaves classically at their own scale, yet each device samples only an approximation to deeper structures. When interferometers measure the tiny stretching of space-time as a gravitational wave passes, they rely on the coherence of light and the stability of distances between mirrors, trusting that any quantum foam beneath those distances averages out over the size of the apparatus. When atomic clocks compare their ticks on Earth and in orbit to test gravitational time dilation, they assume that the underlying network of quantum geometry, if it exists, supports a smooth behavior at those scales. So far, nature has rewarded these assumptions with remarkable consistency. The predictions of general relativity and quantum field theory have survived every precision test in their respective domains. Yet the convergence of thought around the Planck scale keeps the awareness alive that these successes may be like the accuracy of fluid mechanics for describing water, excellent at macroscopic scales, incomplete at the level of molecules. Still, just as no experimenter needs to track each molecule to sail a ship, no astronomer needs a full quantum gravity to chart the motions of galaxies. The limits become most relevant when questions are pushed to extremes, when curiosity probes not how things evolve within spacetime, but how spacetime itself arises. At that boundary, what is measurably stable are not meters or seconds, but patterns of influence, the web of cause and effect filtered through quantum rules and gravitational constraints. The Planck length enters that web as a subtle parameter, setting the grain of the unseen weave, while instruments at human scales trace the larger patterns that emerge from it. The result is a universe in which knowledge is both vast and bounded, where the most distant galaxies and the tiniest particles can be described with high precision, yet where an ultimate infinitely sharp picture is neither available nor required for the world to remain coherent. Far from laboratories and colliders, there exist regions of the cosmos where the questions of smallest distance and highest energy are not hypothetical at all, but written directly into the behavior of gravity. A black hole is often described as a simple object defined by mass, spin, and electric charge, yet this apparent simplicity hides a depth that quietly connects the largest scales of the universe with the smallest. Around every black hole there is an event horizon, a surface from which light cannot escape once it crosses inward. To an observer who remains outside this horizon, behaves like a one-way boundary. Matter and radiation fall through, never to return, while no signal can emerge from within. Classically, the horizon is perfectly black and perfectly silent. When quantum effects are added, a different picture appears. The horizon acquires a temperature radiating faintly in a process that slowly reduces the mass of the black hole. Alongside this temperature arises an entropy, a measure of the number of microscopic configurations that could give rise to the same outward appearance. The remarkable feature of this entropy is that it scales with the area of the horizon rather than with the volume enclosed. When that area is written in units set by the Planck length, the entropy appears to count roughly one basic unit of information per tiny square of Planck size on the surface. In this way, a black hole acts as a concrete embodiment of the idea that the universe measures information in patches of area, not in parcels of volume, and that the Planck length sets the grain of this accounting. Thought experiments imagine a small piece of matter carrying one additional bit of information dropped into a black hole. The mass of the hole increases slightly, its horizon area grows by one Planck-sized patch, and its entropy rises by 1 unit. The detailed internal arrangement that stores this new bit remains unknown, but the external bookkeeping is precise. Each addition of information requires a corresponding enlargement of the horizon measured in these fundamental units. No process can encode unlimited detail into a finite surface without eventually violating this simple proportionality, so the black hole establishes a hard link between geometry and information. The notion of resolution acquires a different flavor here. Instead of asking how closely 2 points can be distinguished in space, the relevant question becomes how finely states can be distinguished on a horizon. The smallest possible change corresponds to one Planck-sized tile appearing or disappearing from the area carrying with it 1 unit of information. Attempts to subdivide this tile further have no meaning in the language of entropy. They would represent distinctions that cannot be recorded by any physical process. In this sense, the horizon embodies a limit on description. Just as the Planck length arises in thought experiments about microscopes and collapsing probes, it arises again as the scale at which surfaces count their information. The connection does not stop there. In holographic theories, the entire behavior of a region with gravity can be mapped to a theory without gravity defined on its boundary. In such a dual description, every event in the interior corresponds to patterns of fields on the enclosing surface. Distances inside translate into relationships between degrees of freedom on the boundary and the maximum amount of information that the interior can hold is already encoded in the finite number of boundary cells measured in Planck units. The same principle that governs black hole horizons then extends to more general regions of spacetime. Any attempt to cram more information into a given volume than the boundary can support would contradict the holographic bound, so the universe resists such compression. The Planck length again appears as the scale of the smallest meaningful pixel in this cosmic encoding. In this light, a black hole is not only an endpoint of gravitational collapse, but a kind of lens turned inward on the rules of information. The smoothness of its horizon at large scales coexists with a discrete structure in how it stores states. The impossibility of seeing inside from the outside mirrors the impossibility of resolving features below the Planck length in any experiment. In both cases, the obstruction is not merely practical. It arises from the way geometry, quantum theory, and information intertwine. The evaporation of black holes through radiation adds another layer. As the horizon shrinks, the information once held on its surface must go somewhere if the underlying physical evolution remains consistent. Various proposals explore how that information might be encoded in the outgoing radiation in subtle correlations spread across many quanta. In some views, the horizon behaves like a membrane that processes information according to rules that respect the holographic bound and the minimal area. In others, the very notion of an interior and exterior is replaced by a more relational description, where the distinction depends on which degrees of freedom are being considered. In each case, the Planck scale remains present as the unit that sets how fine the ledger of information can be written. From the perspective of resolution, these ideas suggest that the deepest feature of reality is not the ability to draw sharper and sharper lines in space, but the way information is allowed to flow, be stored, and be transformed without breaking the quiet constraints encoded in horizons. A black hole, then, is not merely an object that swallows light. It is a manifestation of the fact that the universe keeps careful track of its own possibilities, and that it does so in units no smaller than those set by the Planck length, written softly into the areas of its most extreme gravitational surfaces, across the scale of the cosmos, from the first fractions of a second after the beginning to the slow cooling of galaxies. Now the same quiet balance between energy structure and information keeps reappearing in different guises. The early universe once exists in a state of extreme density and temperature, a sea of radiation and elementary particles interacting so frequently that no stable atoms can form. As expansion proceeds, the average energy of particles falls. Structures that were impossible in the earlier storms suddenly become allowed. First, simple nuclei settle out, then neutral atoms, then stars and galaxies. At each stage, the characteristic energies define what kinds of patterns can persist without being erased. When the universe is young and hot, the wavelengths of typical photons are short, their energies high. They probe very fine scales, but they also disrupt any delicate arrangement they encounter. As the universe ages and cools, the typical wavelengths lengthen. The background light becomes a gentle microwave glow that bathes space without tearing matter apart. The transition from an opaque plasma to a transparent cosmos occurs when photons no longer carry enough energy to ionize newly formed atoms. It is another instance of the same rule. The power of a probe to resolve structures is inseparable from its tendency to modify or destroy them. This balance shapes not only observations made in laboratories, but also the history of everything that condenses from the cosmic fire. On smaller scales within stars, gravity compresses matter until nuclear reactions ignite. In their cores, temperatures and densities allow protons to overcome their mutual electrical repulsion and fuse into heavier nuclei. The energies involved determine which reactions proceed and which are suppressed. In massive stars, the chain continues until iron and neighboring elements form, beyond which further fusion no longer yields energy. When such stars exhaust their fuel, they collapse and explode, seeding space with heavy elements that later build planets and living chemistry. Here too, energy both reveals and reshapes structure, carving shells and cores inside stars, while also driving the processes that end those stars. The ashes of these events drifting in interstellar space cool across millions of years. Dust grains condense, molecules form on their surfaces, and eventually clouds collapse again into new stars with planetary systems. At every stage, from hot plasma to cold dust, the possible arrangements of matter are constrained by the available energies and the ways in which radiation and particles exchange information. The same physics that limits how closely a particle's position can be known, or how finely a horizon can encode information, also governs the balance between order and chaos in these astrophysical cycles. On the scale of a single atom, the rule appears in the spacing of energy levels. Electrons do not orbit in arbitrary paths. They occupy discrete states whose separations depend on the strength of the electromagnetic field binding them to the nucleus. Photons whose energies match these gaps can be absorbed, lifting electrons to higher states, or emitted when electrons fall back. Spectral lines in starlight arise from these transitions. The spectrum of a star is therefore both a fingerprint of its composition and a record of the quantum structure of its atoms. The same discrete nature that forbids arbitrary localization in space also forbids arbitrary energies inside bound systems, and it is this granularity that allows complex matter to exist without collapsing into a featureless smear. Light, in turn, carries these imprints across the cosmos. Its wavelengths stretch as space expands, but the pattern of intensities at different frequencies retains information about the conditions at emission. Telescopes that collect this light function as distant passive probes, obeying the same resolution limits that govern microscopes. Their mirrors and detectors can only distinguish features larger than the wavelength of the incoming radiation, yet within that bound they are exquisitely sensitive. In the faint ripples of the cosmic microwave background variations in temperature of parts per 100,000 encode the seeds of future galaxies. The interplay between wavelength resolution and disturbance is visible here too. Any attempt to probe the early universe with much higher energy radiation would alter the very state being observed, but the ancient light that has simply coasted through expansion acts as a frozen record. At intermediate scales within planetary systems, energy again dictates which arrangements endure. The orbits of planets arise from a balance between gravitational attraction and orbital motion. Closer planets move faster, more distant ones slower, yet each inhabits a band of stability. Too much energy in an orbit becomes unbound, too little and the body spirals inward. The formation of rings, moons, and asteroid belts reflects subtle exchanges of energy and angular momentum among countless small bodies. Collisions and resonances sculpt gaps and clusters, while radiation from the central star modifies temperatures and chemical reactions on planetary surfaces. Even the quiet conditions that allow fragile molecules to assemble in oceans or clouds depend on this delicate web of balances set by gravity, radiation, and the quantum nature of matter. In all these settings, from atoms to planetary systems, one can trace a common whisper. Information is never written arbitrarily finely. The states of matter, the patterns of orbits, the textures of radiation, all occupy a space of possibilities limited by fundamental constants. The Planck length and the associated scales of time and energy do not intrude directly into everyday experiences, but they shape the ultimate bounds within which chemistry, geology, and biology can unfold. They ensure that matter is stable, that photons carry finite packets of energy, and that horizons store information in finite densities. Without such limits, stars might not have finite lifetimes, black holes might store unbounded information, and the smallest particles might splinter endlessly into smaller constituents, preventing any stable atoms from forming. The narrative now looks back across this chain of scales, not to summarize, but to notice how the same relationships play different roles in different regimes. At the smallest distances, the tension between localization and energy shows itself as uncertainty and the possibility of microscopic horizons. At intermediate scales, the same tension shapes atomic spectromolecular bonds and the structure of condensed matter. At the largest scales, it governs how much information horizons can hold, how gravitational waves propagate, and how the universe expands. Distance, once treated as a simple backdrop, becomes a derived notion emerging from these interactions rather than dictating them. Energy, once a measure of capacity to do work, also measures the capacity to disturb and the capacity to encode information. Light, once thought of as a carrier of images, only reveals itself as a participant in setting the limits of what images can exist. In this way, atoms, light, and the universe as a whole follow the same quiet rule. Finer detail requires higher energy. Higher energy deepens curvature and spreads information over horizons or fields, and beyond a certain point, the very effort to see more transforms the stage itself. The cosmos does not forbid curiosity, but it channels it along paths where questions about ever sharper distances gradually transform into questions about patterns, correlations, and the gentle constraints that keep reality from fragmenting into infinities. At this stage in the quiet exploration, the idea of resolution itself begins to feel less like a technical term and more like a thread stitching every scale of reality together. Microscopes, colliders, gravitational wave observatories, cosmic background mappers, all are attempts to draw an image of the universe with finer and finer lines. Yet the closer this image approaches the Planck scale, the more clearly it reveals that something subtler than distance is at work. Every tool that sharpens a picture does so by coupling energy to matter and to space-time, and every such coupling leaves a trace. In the earliest experiments with light and glass, that trace is gentle, a slight warming of a sample under a lamp. In modern particle physics, it is a transformation of particles into showers of new ones, a rewriting of the very configuration under study. If the energies were ever pushed near the Planck regime, the trace would be stronger still, a distortion of geometry so intense that the region being probed could vanish behind a horizon. The story that has unfolded suggests that the universe tolerates this sharpening only up to a point, and then quietly shifts the rules. Below atomic scales, particles cease to behave like tiny marbles, and instead occupy clouds of probability. Below nuclear scales, protons and neutrons cease to look like compact beads and reveal seas of quarks and gluons. Below those scales, even the concept of an independent constituent begins to falter as fields dominate and proposals for deeper layers remain speculative. The attempt to press on with the same mental picture of smaller and smaller objects in ordinary space meets resistance not because curiosity is unwelcome, but because the assumptions behind that picture no longer hold. Quantum mechanics dissolves the notion of exact trajectories, replacing them with amplitudes that spread and interfere. General relativity dissolves the notion of a rigid background, replacing it with a space-time that bends and responds. At the Planck scale, these dissolutions overlap. The path of a particle can no longer be drawn on a fixed stage because the stage itself is stirred by quantum fluctuations. The intuitive hierarchy of object on background gives way to a mutual dependence where field geometry and information define one another. In such a regime, a question like how far apart 2 points are becomes inseparable from questions about how much energy is present, what correlations exist, and how horizons form. The smallest meaningful distance is then not a hard brick wall in space, but the place where further refinement of geometric language stops increasing understanding. Instead, other descriptions begin to carry more weight, descriptions that speak of entanglement patterns, spectra of possible states, and limits on information flow. Seen in this way, the Planck length functions as a change of vocabulary. Above it, distance, time, and curvature are excellent words for organizing experience, just as temperature and pressure are excellent words for describing gases. Below it, those words lose sharpness, just as temperature becomes less meaningful when a system contains only a few molecules. What remains consistent are the deeper relations, conservation laws, symmetries, and the ways probabilities add and interfere. Theories that venture into this deep regime, whether they use strings, loops, or other constructs, all attempt to phrase reality in terms that remain sensible when the continuum breaks down. They differ in their details, but share a recognition that classical notions must emerge as approximations, not as exact premises. This perspective has a calming implication for the long arc of inquiry. The absence of an infinitely sharp picture is not a failure. It is a structural feature of a universe that remains finite, stable, and capable of complex organization. If positions could be defined with arbitrary precision without cost, energies could diverge, horizons could store unbounded information, and many processes that now lead to equilibrium might not converge. The same limits that frustrate the dream of infinite zoom also prevent runaway behaviors in both microscopic and cosmic systems. Atoms maintain stable sizes, stars have finite lifetimes, black holes hold information in proportion to their surface areas, rather than collapsing the bookkeeping of physics. In this sense, the Planck scale acts as a regulator woven into existence, taming infinities before they can break the coherence of the whole. The narrative that tracks this scale from thought experiments about microscopes through the interiors of protons around the ring of colliders and outward to the horizons of black holes finds a consistent theme. Resolution is never free. Every gain in clarity demands energy, and beyond a certain point that energy ceases to reveal and begins to reshape, then to conceal. The deepest question then shifts from what sits beneath the last visible layer to why the layers arrange themselves so that visibility has a limit at all. Perhaps the answer lies in a principle of sufficiency, where the laws of physics organize information so that rich structures can form without requiring an infinite cascade of smaller and smaller scaffolds. Perhaps it lies in some still unarticulated property of quantum gravity that makes space-time itself an emergent, self-limiting construct. Whatever the final theory, the path traced so far suggests that when rulers fail, the universe does not end in chaos, but in a different order, one that trades distances for relationships and offers a kind of clarity that is not about sharp edges, but about understanding why edges cannot be sharpened forever. In the end, the journey toward the smallest scales draws a wide circle, beginning with the largest structures that telescopes see, and returning quietly to the instruments and minds that first ask how finely the universe can be resolved. Galaxies drift apart as space expands, clusters fall together under gravity, and filaments of dark matter stitch a cosmic web across billions of light years. Within that web, stars light up, planets cool, and on at least one world, questions arise about what all of this is made of. The route from those questions to the Planck length passes through lenses, beams, crystals, magnets, and equations, each step translating curiosity into a more refined way of focusing energy and extracting information. It is tempting to picture this route as a downward ladder made of smaller and smaller pieces, molecules within cells, atoms within molecules, nuclei within atoms, quarks within nuclei. Yet as the narrative follows this descent, the rungs grow less like solid bars and more like patterns in fields until at the lowest levels the distinction between object and interaction fades. In practice, the universe continues to be explored far from this frontier. Telescopes extend vision deeper into cosmic time, capturing light that has traveled for nearly the entire age of the cosmos. Gravitational wave detectors listen to faint tremors of space-time as massive bodies merge. Precision clocks compare their rhythms on Earth and in orbit, refining the map of how time flows in curved geometry. Underground instruments wait for rare interactions with unknown particles that might make up dark matter, while high-energy observatories scan the sky for cosmic rays and gamma-ray flashes. None of these devices can touch the Planck length directly, yet all constrain how any theory operating at that scale must match the universe that is actually observed. In parallel, theoretical work revises and extends the language used to describe what might lie beyond the reach of classical geometry. Some frameworks begin with strings and branes vibrating in higher dimensional spaces, others with discrete networks of quantum geometry, others still with patterns of entanglement from which distances and even time are emergent. Each proposal treats the Planck length not as a point to be reached, but as a scale at which traditional descriptions must hand their role to new concepts. Their success is judged by how gracefully they recover familiar physics when coarse-grained back to larger scales, and by how naturally they incorporate the limits on information and resolution suggested by black holes in cosmology. The emerging picture is that there may be no single answer to what space-time is at its deepest level, but several complementary ways of encoding the same relational structure. For a mind following this story in the stillness of night, the most striking feature may not be any particular mechanism proposed for quantum gravity, but the way the same quiet constraints echo from scale to scale. The rule that to reveal finer detail one must use higher energy appears in microscopes, in colliders, and in the history of the hot early universe. The counter-rule that concentrated energy inevitably curves space-time and can hide what it creates behind horizons appears in the formation of stars and in the collapse to black holes. Between these tendencies, a balance emerges, one that allows rich structures to form and persist without requiring infinite resolution. Atoms are stable because quantum rules prevent electrons from spiraling into the nucleus. Stars shine for long spans because nuclear reactions and gravity reach equilibrium, and black holes store information in finite densities set by their areas. Seen from this angle, the Planck length is less an obstacle than a quiet assurance that the world is constructed in a way that avoids the paradoxes of unbounded divisibility. It marks the point where attempts to think in terms of finer and finer spatial subdivisions cease to add clarity, and where questions about patterns, correlations, and information flow become the more natural language. Curiosity does not have to stop at this boundary, it shifts focus. Instead of asking what lies beneath space-time in the sense of smaller pieces occupying smaller regions, it asks how space-time itself might arise from more primitive relationships, and how the laws that govern those relationships manage to produce a universe that is both stable and capable of complexity. In control rooms and observatories, screens glow with traces of particles and distant galaxies, each pixel a record of some interaction between matter radiation and the instruments built to receive them. The data arrive in finite streams, carrying limited information, yet from the models of cosmic history and microscopic structure are inferred. No measurement is infinitely precise, no map infinitely detailed, but the patterns that emerge are reliable enough to guide spacecraft and retrace the evolution of stars. The recognition that there is a smallest meaningful distance does not diminish this achievement. It frames it and suggests that knowledge in this universe comes in finite, well-structured portions. As the narrative settles near this idea, the images of quantum foam strings, loops, horizons, and emergent geometry recede into the background like constellations seen through a soft blur of atmosphere. Each offers a pathway toward understanding how rulers eventually fail and how another kind of clarity takes their place. The Planck length remains as a quiet threshold, not a wall, but a change in the way questions must be asked. Between that frontier and the largest cosmic structures, there is room for stars, planets, and thinking creatures to arise, wonder, and rest, while the deepest structures of reality continue their silent work beneath the reach of any instrument.